Okay, in this unit, in your 143 class, you're going to be talking about probability, odds, things like that. So we're going to start by looking at some basic definitions to make sure you understand them. Because as far as probability goes, you need to know definitions, and then you need to know a few basic formulas. Probability can get really, really complex, but I don't think you're going to bother with that in 143. So we want to make sure we understand the definitions and can write everything out correctly according to definition, and can then apply a few rules of probability. So first off, we all kind of understand what probability is. I flip a coin, what's the probability I get a head? I'm assuming you'll all say 1/2. I roll a die, what's the probability I roll a 4? I'm assuming you'll all say 1/6. So we kind of understand the basic idea of probability, but as far as definitions and terminology goes, basically the idea is you start with an experiment, you're going to do something. Let's see, for my experiment, I could flip a coin, or I could roll a die. We'll just use those two. Once I have an experiment, then I get outcomes. As far as outcomes go, it's just what happens when you perform the experiment. So in this case, if I flip a coin, the possible outcomes are heads or tails, H or T. If I roll a die, I could get a 1, 2, 3, a 4, a 5, or a 6. But then as far as the terminology we use in probability, we talk about what's called a sample space. The sample space is just all possible outcomes for your experiment. And normally we write it in set notation. I don't know if your instructor in 143 will do that, but it's kind of the standard in probability, so we'll go with it. And all you do is, you look at your outcomes, and you put them in curly braces like that, which is set notation that we use for probability. So the sample space for flipping a coin are the possible outcomes, heads or tails. The sample space for rolling a die, 1, 2, 3, 4, 5, 6. And then, once you have an experiment, you have the sample space that lists all the outcomes, then you can start generating a probability. But before we do that, we want to mess around with sample spaces to make sure we kind of fully understand experiments we do and the outcomes that you can get. Meaning, well, we'll start with these two right here. Flip a coin. For the sake of argument, suppose I flip 2 coins. What are the outcomes there? And the way we think about this from a probability standpoint is really, if you're going to do multiple things, you're going to do one, then you're going to do the other. Then you'll do something else, then you'll do something else. Meaning, if I'm going to flip 2 coins, I flip a coin and I record the outcome. I flip the other coin and I record the outcome. So what outcomes are there here? Well, if we think about it, I could flip the first coin and get a head. Then I could flip the first coin and get a tail. I could flip the second coin and get a tail. So I could get a head, then a tail. I could flip the first coin and get a head. Then I could flip the second coin and get a head. So I could get a head and then a head. And then I could flip the first coin and get a tail, flip the second coin and get a head, or flip the first coin and get a tail, flip the second coin and get a tail. And again, the idea here is, if you flip 1 coin, you get a head or a tail. Once you flip multiple coins, or if you flip 1 coin multiple times, you essentially have to record what happens the first time you flip it, what happens the second time you flip it. So here, my outcomes would be head, 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 tail, tail, head, tail, tail. And my sample space would be head, 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 tail, tail, head, tail, tail. But the problem is, all things being equal, you will solve problems like this, but from a math perspective, well, those get really boring really quickly. So instead of flipping 2 coins, maybe we want to flip 10 coins. How many outcomes are there? And how do you go about finding them? There's different ways to go, but one standard trick will do it with 3 coins, flipping 3 coins, is what's called a tree diagram. A lot of times in probability, when we have to count outcomes, or in counting problems, it's called combinatorics in math, when we have to list things out, we use tree diagrams. And the idea is, if I'm going to flip a coin 3 times, I start right here, I flip the coin the first time and I record the outcomes as 2 branches. So we say I can get a head or I can get a tail. Now, when I flip the coin the second time, what can happen? I can get a heads or a tails. So I create new branches at the end of each of these for head and tail. Then what happens when I flip the coin the third time? I can get a head or a tail again. So I create branches at the end of each of these for heads or tails. Now I've listed out all my flips. There's the first flip. There's the second. There's the third. Now I just go along each branch to record the outcomes. And here, if I just run down the list, head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. And there's all my outcomes. In this case, I get 8 of them. And instead of rewriting it, I'm just going to do that in set notation. And there's my sample space of all possible outcomes. These can get messy really quickly. I mean, here, it's pretty much the easiest experiment I can do. Flip a coin 3 times, and already I've got 8 branches. If I flip a coin a 4th time, head, tail, 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 I'll actually end up with 16 outcomes. So they can get really cumbersome really quickly, but they actually help a lot, at least as far as helping us see all of our outcomes. And while we haven't actually done it yet, what if I was asked, what is the probability that if I flip a coin 3 times, I get 2 heads? Well, now I can just run down the list. There's 2 heads, there's 2 heads, there's 2 heads, and I'm done. And my probability is easy to find. So these tree diagrams are very helpful, but they also get really cumbersome really quickly. They also give us another trick that we use a lot for counting. And you can use this in different areas of math and even without tree diagrams, but it's easiest to see with the tree diagram. So I'll just mention it now since we're doing it. It's what's called the multiplication principle. And all it really says is, if one experiment can be done in m ways, and another experiment can be done in n ways, then together, both experiments can be done in m times n ways. And the idea is, well, right here, perform an experiment. Say this one right here. This experiment can be done in 2 ways. I flip a coin, I get 2 outcomes, heads or tails. Perform another experiment. My second experiment is to flip the coin again, and I get 2 outcomes. I repeat it twice because of the tree diagram, but there's 2 outcomes, heads or tails. According to this, while the first flip can be done in 2 ways, The second flip can be done in 2 ways. So together, the first 2 flips can be done in 2 times 2 ways, 4, which is what we saw. We had 4 outcomes when we flipped twice. Here, if I add a third experiment, flipping the coin again, the same principle would work. Maybe I say M, N, and the third experiment can be done in O ways. Then you would get M times N times O. Or, there's 2 outcomes here, there's 2 outcomes here, there's 2 outcomes here. All told, 2 times 2 times 2, 8 possible outcomes, which is what the tree diagram gives us. Once you understand the concept, then it allows you to count things really quickly, because you just say, how many ways can I do this? How many ways can I do that? And done. A couple more quick examples before we move to something else. Roll 2 dice. How many outcomes are there? And list out the sample space, which I'm not going to do. It's on the paper that you're going to do. This one is going to be up to you to write out. But think about it. If I'm going to roll 2 dice, that's 2 different experiments. How many outcomes do I get the first time I roll? Well, 6. How many outcomes do I get the second time I roll? 6. So if I roll 2 dice, there's 36 different outcomes. You could draw a tree. First branch, you'd have 6 possible outcomes. Second roll, you'd have 6 branches on each of these. I'm sketching that quick because I'm not going to do it. Easiest way to list these out, I can get a 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Meaning, I roll a 1 on my first roll. On my second roll, I get a 1, 2, 3, 4, 5, or 6. But then, I can get a 2 on the first roll, and I'll do the pattern again, from 2, 1 to 2, 6. Then I'll do 3, 1, all the way down to 3, 6. Over to 6, 1, down to 6, 6. And yes, you should write all these out. You're going to have to for one of your worksheets, because you're going to be using this one a lot, which is actually why I'm not writing it out, because I want you to, because it'll help you. But we can kind of see the grid here. There's 6 entries here, 6 entries here, 6 entries here. Clearly, I didn't list them all, but there'll be 6 columns. 6 columns, 6 rows, 36 total outcomes. But you can expand on this, and you're going to do this on your worksheet. You actually have 2 this week. Let's see. I pick an outfit to wear. Believe it or not, I have something other than a Superman hoodie that I actually wear. Okay, pick an outfit. I have 3 pairs of pants, 4 shirts, and 3 ties. How many outfits can I make? And by an outfit, we obviously mean a shirt, a pair of pants, and a tie. There's 2 ways we can do it. One way is to say, I'm going to draw a tree diagram. I have 3 pairs of pants. So first pair of pants, second pair of pants, third pair of pants. Then I have 4 shirts. So I have 4 shirts at the end of each pair of pants. Then I have 3 ties. So I put 3 ties at the end of each shirt. And you could list all those out and then count all the branches, or multiplication principle, 3 pairs of pants, 4 shirts, 3 ties, 3 times 4 is 12 times 3. There's 36 different outfits. Ultimately, you should be able to both write out the tree diagram and list out the entire sample space, all 36 of them, but then you can use the counting principle to make sure you're listing everything out. This video was long enough. I'm going to make another one doing more probability and counting type stuff.